Hello, and welcome back to Introduction to Genetics and Evolution. In the most recent videos, we've been talking about how you map a simple genetic trait. So a trait whose variation is caused by variation at a single gene. In the previous video, we talked about mapping a simple genetic trait using a cross, or basically a pedigree. In this video, we're going to take it a little bit further. We're going to look at a different sort of genetic mapping. But let me stress, the underlying principle of all genetic mapping, including what we'll be talking about in this video, is an association between genotypes at markers, so having, big A, or little a at a particular marker, and the appearance of a trait or disease. Okay? So let's look at this. Can we map diseases without controlled crosses or pedigrees? This is a big question. Now, obviously, it's not socially acceptable to force people to mate with others, especially ones who may have diseases. So if you wanted to map the genetic basis of, say, predisposition to some sort of cancer, you can't find, well, here's a cancer person, here's somebody who's a carrier, let's make them have kids, things like that. That obviously would never fly. And you also can't always find enough subjects who happen to have bred in an informative way, right? You can't find these individuals you can't find tons of people who have a particular kind of cancer and happen to have kids with somebody who was a carrier for the same sort of thing. So is there another route? The answer is yes. What we can do is we can leverage population data over time. Now, on average, this is a just broad off-the-cuff average, the human generation times historical average is on the order of about 20 years. Okay? So when we looked at recombination previously, we were looking at what happened in one individual. So basically, we were looking at a time frame in total of about 20 years, or one generation, one bout of meiosis, one iteration of some crossing over. Now, when you're looking at genes that are very close together, so genes that are maybe thousands or even tens of thousands or even potentially hundreds of thousands, there's a very basis apart. There's a very low probability of having a crossover between them. There's a very low probability of exchange. Now, if you're looking at bases that are, say, hundreds of thousands of bases apart, although there's a very low probability of exchange in one generation, if you look over the thousands of years of human history, there actually has been a lot of recombination. So just putting in a little bit of math to it, if the probability of exchange is only 0.1%, so it's very low, in one generation between, say, two SNP markers, there would actually be a 99.3% probability of exchange when you iterate that over 5,000 generations. You can think of it like flipping a coin. That, yeah, your odds are 50% of getting heads with one coin flip. But what are your odds of getting heads if you flip the coin 50 times, that you get at least one heads? It's very, very high. Same sort of thing happens even when you have very low probabilities of exchange. Now, over human history, most neighboring genes will have had their alleles shuffled. And this will be true even for very close genes, but even sometimes within genes. You'll actually find some areas inside a gene that will actually have a crossover event. So you'll have, for example, the father's copy and mother's copy. You'll have a crossover event that makes it so this end of mother's copy links up with this end of the father's copy. Now, let me show you this with a picture. So let's imagine we're starting a population with 4 chromosomes. Let's say that, going to this island, we have 2 individuals. One of them is heterozygous blue over red, and one of them is heterozygous brown over purple. And they, the Adam and Eve of this island basically start a population, and their kids have kids, their kids have kids, etc., etc., and they live on this island for many, many years. Okay, so we have these 4 chromosomes that started everything. It happens to be that the blue chromosome has a disease-causing mutation, right? So that's this little star that's under the D in the blue. Well, let's say we have some genetic markers, so we can look at genotype at marker 1 and see if it's blue, red, brown, or purple. And we can look at genotype at marker 2 and say it's blue, red, brown, or purple. Okay? And what we see is that after all these generations, after many generations, instead of having one crossover event that's happened, we have this sort of shuffled up chromosomes, as you can see here. Depending on how many generations, you may actually see a lot more shuffling than is depicted here. But this is sort of a moderate amount of shuffling there. So this might be after, say, hundreds of generations rather than thousands of generations. We see this sort of shuffling in here. Now, what you see nonetheless, even though there's been this shuffling, we see the same principle that we saw before with genetic mapping and crosses. That things that are very close to each other tend to remain associated. Things that are farther apart don't have that same tendency. So when we look at D and M1, you tend to have the same type there, that blue with blue, brown with brown, red with red, purple with purple, blue with blue, etc. For D and M2, we don't see this association. Here it's red with purple, blue with brown, brown with blue, etc. They've become dissociated from each other. D and M2 have become associated, whereas D and M1 remain associated. So we can actually, if we can genotype what's going on at markers 1 and markers 2, we can still see an association between genotype and phenotype. In this particular case, the ones that have the blue allele at marker 1 are likely to have the disease-causing mutation as well. Now let me build on this with another facet. Recombination, actually, or the crossing over, is not homogeneous when you look at a very, very fine scale. So far we've been looking at whole chromosomes, and we see one crossover event in one generation, sometimes two, things like that. But if you look at a very, very fine scale and over very long periods of time, you see these crossovers don't just happen completely randomly, but there are a couple of spots across the chromosome that they tend to happen. These are referred to as hot spots of recombination. You find them every few thousand bases in humans, and the rest of the genome basically has a recombination fraction, or RF, of 0, that you essentially don't see recombination in these different areas. So looking at this is a stretch of genes across one human chromosome, and this shows you the recombination fraction. These peaks in recombination are crossover hotspots. So you see, for example, there's a crossover hotspot here between DMB and PSMB9. So you might expect over a very long time, this is a place where a crossover may happen, and DMB can become dissociated from PSMB9. In contrast, PSMB9 and TAP1, they're both very close to each other, and there's no recombination hotspot. So even over a very long time, it seems like these two are likely to be stuck together. They're in the same window between these two peaks. You can think of these peaks as defining a boundary. And in here, in this window part, you essentially have recombination of 0. But here in these peaks, you do have recombination. So this can become dissociated from this, but this cannot become dissociated from that. So what are the implications of this? And I'll show you an application of this so it'll make a little bit more sense in just a moment. Well, we have shuffling occurring between these windows every few thousand base pairs. Let me emphasize, when I'm saying that shuffling is occurring, I don't mean every generation it happens. I just mean there is some chance that over thousands of generations you can have this shuffling. You can have a crossover event happen at one of these hotspots, potentially once or a few times every couple of thousand generations. But in contrast to that, we have some areas where no shuffling is occurring, and those are the areas within the windows, the areas between the recombination hotspots. There is basically no recombination. Or you can say that they are in linkage disequilibrium. This is often referred to as LD. They're in linkage disequilibrium. Essentially, the alleles at one are stuck with the alleles they started with at the other one. Now, some of these windows are going to contain genes that have alleles causing disease. And what we can do is we can leverage these recombination hotspots and windows between them to find the disease-causing genes. And let me illustrate this with an example. Now, again, as we said, we have these windows within which recombination doesn't happen, and we have recombination hotspots where recombination can happen. So I've depicted here, this little lightning bolt indicates a recombination hotspot. Now I've made it so the recombination hotspot is only one base long. That's not actually true, but let's just pretend this for the second. So I'll draw a line down here and saying that is the site that recombination can happen sometime over the course of thousands of generations. Now, within these windows here, so between recombination hotspots, maybe there's another one over here. Within these windows, you won't have recombination. So what you'll see is there will tend to be an association between the genotypes at these SNPs. So let's look at, for example, SNP1. The C is associated with G, the T is associated with C, C with G, C with G, T with C, etc. So you see that there's a strong association there within one of these windows. Now let's look between windows. So let's take SNP3 and SNP4. So this is in one window, this is in a different window. A is with G. In this case, G is with G. In this case, A is with G, A is with C, G is with C. So we see that over the course of time, the alleles in this window have become dissociated from the alleles in this window. However, within the windows, these different SNPs stay very strongly associated. Now, in this particular case, we have one causing a disease. Now, let's focus on that. Now, let's pretend we didn't look at all these SNPs. Let's just look at a couple of them. Make it a little bit simpler here. What we see looking at this is that if you're looking at for an association between genotype and phenotype, which is what we're always trying to do with genetic mapping, we see here that this individual would have the disease because it has this A mutation. And we don't actually know this A mutation because we're not looking at it. We're only looking at the SNPs. But Gs tend to have the disease mutation. Cs do not. This G actually is okay. This G has the disease mutation. C is not. C is not. So we see that on average, if you have a G, you're more likely to have the disease. If you have a C, you're very unlikely to have the disease. So there is an association here between the genotype at SNP2 and whether you have the disease. And that's because SNP2 is linked to the mutation causing the disease. Now, let's try the same thing with SNP5. In this case, an individual with T has the disease. This individual with T does not. T does not. A has the disease. A does not. A does not. There's no particular association between the genotype at SNP5 and whether you have the disease. And the reason for that is because when you're looking, even over the course of many generations, SNP5 has become disassociated from the disease-causing mutation. Okay? So our prediction, again, is that, like with all genetic mapping, the disease gene mapping is associating the genotype, and this is looking at the markers, in this case the SNPs at one location, with the phenotype, which is the disease. Now, we don't know the SNP or the mutation causing the disease. We're trying to figure out where it is. If a marker is very close to the disease-causing gene, then individuals having one allele at that marker will be more likely to have the disease than individuals having a different allele. Essentially, the marker will be in LD, or in linkage disequilibrium, with the disease gene. And this does not mean, I want to emphasize that, this does not mean that the marker gene or SNP causes disease. So that the answer to this would be a very resounding no. This is a common misconception. People say that, oh, look, that's associated with the disease, and therefore that causes it. No, it just means it's in linkage disequilibrium with the alleles causing. So let's give you an example to try this out. Let's say that you're trying to map irritable bowel syndrome. And you're sampling population for alleles of 2 markers, and you're looking at incidence of this disease. Now, just to make things a little bit simpler, we're just going to forget the heterozygotes. So we'll just go with big A, and little a, little a. Okay? So big A individuals, you look at 100. You look at 100 individuals, and 20 of them have IBS. Little a, you have 200 individuals, and 40 have IBS. Is there an association between genotype and phenotype? Well, you might say yes, because look, a lot more of these have IBS. On the other hand, you sampled more individuals. Let's look at what actually is going on here. In this case, out of 100 individuals, 20 have IBS. So your probability of having IBS in this case would be 20 over 100, which is equal to 0.2. Okay? For little a, you have 40 out of 200. So again, your probability of having a disease is 0.2, 20%. So there really is no association between the genotype at SNP1 and the disease. So we can just cross this out. What about SNP2? Well, here we have 50 individuals, 45 have IBS, or 250 individuals, 15 have IBS. Well, let's look at this now. In this case, we have 45 over 50 for a big B. For a little b, we have 15 over 250. That's a huge difference. You can do the math there. That's a huge difference between those two types. So in this case, we can say that the genotype at SNP2 is associated with irritable bowel syndrome. This does not mean that SNP2 causes it. It just means that SNP2 is probably closely linked to a gene that causes it. And it could be. It could be that SNP2 actually does cause it, but it's improbable you would happen to have just found that. So, I won't rule it out, but in this case, SNP2 is associated with it. SNP2 must be near the disease-causing mutation, or possibly, but unlikely, it could be it. Now you may be thinking, the genome's a big place. There's over 3 billion bases in the human genome. And if there's a hotspot, as I mentioned before, every about 3,000 base pairs, how many markers would you need to study to find disease genes? So basically, how many windows are there? So there's 3 billion bases total. There's a hotspot every 3,000 base pairs. How many markers do you need to find them? Well, the answer is pretty simple. Basically, you just divide this by that. So essentially, you need about 1,000,000 markers. You need about 1,000,000 markers to sample the whole genome to try to find a disease-causing gene, given these windows. Now, that may sound very difficult, but technology helps. In fact, this is really not a problem at all now, thanks to recent innovations. We have microarray chips that can actually tell us the genotype of over 1,000,000 markers at once just from your spit. This is what some of the companies I mentioned a while back, like 23andMe, do when you send them that little tube of your spit. They basically are genotyping you for over 1,000,000 markers. And they'll do this for you at a fairly low cost, and they can tell you from that your susceptibility to many mapped diseases. They're basically using published data on those diseases, and they're mapping. Now, let me give you an example to try. I give you here 1,000 people, 950 of them are healthy, and 50 of them have cystic fibrosis. You're trying to map, if there's a gene associated with any of these markers that may be causing cystic fibrosis. So I want you to go ahead and try it out and do the same sort of thing that we just did and see, are any of these markers, possibly more than one of them, associated with the gene contributing to cystic fibrosis? Well, hopefully that wasn't too challenging. Let's give it a shot and see where is the strongest association between genotype and phenotype. Okay, and normally you'd want to do some statistics with this. We're going to skip the statistical facets. We just want to see where do you see the strongest association. Okay. Now, in looking at this, let me just do two of them. I'll do one negative and then I'll do the right answer. So this first one, you're looking at, let's say for example, 600 of these 1,000 people have the big A allele, 400 of them have little a. Among the ones with big A, 28 have cystic fibrosis. So just put out your calculator and say, what fraction of big A individuals have cystic fibrosis? That'd be 28 divided by 600. And that would be 4.6%. Okay? So what about for little a? Well, we've got 22 divided by 400. That is 5.5%. So maybe there's a little hint of an association, maybe not. That could just be random. Again, we're not going to worry about the statistics. I just want you to look for where's the strongest association. Now let's look at marker 3. There we have 45 out of 100. So 100 people have big C, 900 have little c. Again, we've just pretended there are no heterozygotes. Okay. So for the first one, it's 45 divided by 100. Well, I can do that one in my head. That would be 45%. Okay, so among big C, if you're big C, your odds of having cystic fibrosis is 45%. What about little c? Well, it'd be 5 divided by 9. 5 divided by 900. That would be 0.5. Well, that's a huge difference from 0.5% to 45%. There's basically a 90 times higher chance that you have cystic fibrosis if you're a big C than if you're a little c. So clearly in this case, there's a very strong association of marker C with cystic fibrosis. So what does this mean? The big C genotype at marker 3 causes cystic fibrosis, right? Wrong. It is not the case. It is linked to variation causing this. Now, one question you may be wondering is, why do some people with little c still have cystic fibrosis? In fact, why doesn't everybody who's big C have it? Well, there's many answers to this, and this comes back to the italicized word in our video title, right? I said we were mapping very simple genetic traits, but simple is sometimes somewhat unrealistic, right? That you can have environmental effects. A lot of diseases have multiple genes contributing to them, and we'll talk about, as we go into some of the subsequent videos, some of these confounding factors that make it so a lot of the mapping is not as simple as I've made it to seem here. But sometimes you are lucky. Sometimes there are traits or with allelic variation that is very strong. Now let me conclude this video with just a quick recap. Now this is showing you the distinctions between association mapping in a population like we just did, and the cross pedigree mapping as we've done in previous videos. Now with a cross, you're mapping in known families, so you're taking individuals that, for example, are carriers and seeing what happens when they have kids with individuals that have the disease, or maybe carrier with carrier. Your resolution, just to give you some idea how precisely you can localize these genes causing the disease. This is just a ballpark. This is not a dogma. You're looking at a resolution of about 2 million base pairs. You've narrowed it down from the whole genome to about 2 million base pairs. It's better than nothing. In this, for crosses, you have one generation of recombination. You're looking at just one bout of crossing over. And importantly, this actually works fairly well even if the mutation is rare in the overall population. So that is actually a plus for you. With populations, you're actually, rather than mapping in known families, you're mapping across a population. Right? You're just taking a bunch of unrelated individuals. They just all happen to be in the same species in the same population. Your resolution here is much better. Rather than 2 million base pairs, your resolution here is about 3,000 base pairs, because it's about that of those windows between the recombination hotspots. Importantly, the reason that you have so much higher precision here is because here you're leveraging many generations of recombination, whereas in the cross you're leveraging one generation of recombination. So your precision is higher because you've allowed many more recombination events to happen, and therefore you can more precisely localize what's going on. Now, the downside to this one is this doesn't tend to work if the mutation causing the disease is very rare in the population that you're studying. Now, one question people often ask is, what is the recombination rate between the two sides of the hotspot? They think it's something like 10 centimorgans or 10% recombination. No, let me emphasize. For reference, the recombination fraction across a hotspot in one generation is probably less than 0.01 centimorgans. This is why you have to look across many, many, many generations of recombination to see any effect from them. Well, I hope this was helpful. Thank you for joining us.